Welcome back. In the previous lecture, we introduced the position operator. In this lecture, we consider infinitesimal changes of position and so identify the momentum operator that teams up with the position operator. So we continue with discussing this situation of a particle moving along the x-axis. And so we have the brass x, and we ask, how does this bra change if I change the x, the label a little bit? So how does the bra that refers to one point compare with a neighboring one? And as always, rather than just saying what is x and what is an x prime, how are they related, we are looking at a small change in x. So let me write down an x plus a small change epsilon. And so this has to come about, since if I shift all the x's by the same amount epsilon, well, then I turn the whole basis of x bras into another basis, which is just obtained by relabeling them a little bit, okay, shifting the whole basis by an epsilon. So this must come about by applying a unitary operator to the original x. Now this unitary operator will be of the form e to the I times a Hermitian operator. And for this Hermitian operator, well, it should be proportional to this epsilon. And then it's shifting position. So we borrow terminology from classical mechanics and call this the momentum. So remember when we were talking about changing time by a small increment, we had the energy, the Hamilton operator. Now we're changing the position by a small amount, and then that goes with the momentum operator, the small amount epsilon. And so epsilon is an increment in position, so this is a length times momentum. That has the metrical dimensions of an action, so we divide by Planck's quantum of action, h bar, to make sure that this exponential argument, the argument of the exponential function, does not have a metrical dimension, it's just a number. And we need the I to make sure that for this self-adjoint Hermitian momentum operator P, we get a unitary transformation. So this is just writing down what momentum means. It's the operator that shifts position. Okay, and that's just terminology that we borrow from classical mechanics. Now, since we're looking at very small changes, I'm just taking this unitary operator to first order in epsilon. And then it will be x, and here we have 1, the identity, plus I divided by h bar, epsilon p, and then there are higher order terms which we are not interested in because we are now looking at an infinitesimal, by which I mean a very small epsilon, a very small shift from x to a neighboring x. All right? On the other hand, if it's a very small shift, this will be equal to the original x plus epsilon times the derivative of that original x, which is just the first two terms of the Taylor expansion. So by now comparing the two expressions, we find that the action of the momentum operator on the position bra, which we have here, is equal to, removing the common factor of epsilon, is equal to h bar divided by I, the x derivative of the position bra at x. So it tells us how we get a small change in x. So if I compare x with a neighboring x prime, so this x prime is now an x plus epsilon, and I want to say, aha, so how does this differ from that? Well, it differs by epsilon times the x derivative, and that's obtained or given by applying the momentum operator to the position bra. Fine, so we have this statement. And then, of course, we also have the adjoint statement where we apply the momentum operator to a position ket. And that again will be a derivative, but it's now differentiating the ket. And because we have to take the adjoint, so a complex conjugation is involved, we will get I times h bar rather than h bar divided by I, which is multiplying by negative I. And then we have the derivative of the position ket. So here we have the action of the momentum operator on a position bra. Here we have the action of a momentum operator on a position ket. So let's see what happens if we apply the position operator and the momentum operator to a position bra. So first I will work out what is the outcome when I take the position bra and I apply the position operator and then the momentum operator. And then later we will see what happens if I apply the momentum operator first and the position operator later. So here it's very simple. So first we apply the position operator, well, that gives us the value x, and then the p is applied. And here we read off, this is x, and then h bar divided by I, the derivative with respect of the x bar. Now here we begin with h bar divided by I, the derivative of x, the position bra, and then the position operator is applied. But now we apply this and it becomes a number. And so what is now differentiated is the number x multiplying the bra at x. And so there is a term where I differentiate the bra, that is x h bar divided by I, the derivative of the bra. And then from the product rule, there's a second term where I differentiate this x, and that just gives us h bar divided by I and bra at x surviving. Okay, so now this is exactly the expression that we have here. So here we have x and then p x applied followed by applying p plus h bar divided by I times the identity applied to x. So this is equal to this expression. So here we apply the momentum operator to the position bar, then we apply the position operator to what we get from applying the momentum operator. Here we apply the position operator to the position bra, and then we apply the momentum operator to what we get from applying the position operator. And then there's an extra term where we just apply the identity. But these things have to be the same, and they have to be the same for each of these position bras. And since the collection of the position bras is a complete set, the two operators have to be the same. So what we have found here is the following statement, that position operator times momentum operator plus h bar divided by I is equal to momentum operator times position operator. Now if I bring this over to the other side, then we have xp minus px. Well, that's the commutator of x and p. I bring this over to the other side, and this will be negative h bar divided by I, or I times h bar. And so what we have arrived at here is a very famous commutation relation for position and momentum that was found by Heisenberg with some help provided by Born. So it's known as the Heisenberg commutation relation for position and momentum. So here I just quickly summarize what we have discussed a minute ago. We have the position bra, we apply the momentum operator, it differentiates the position bra and as a factor of h bar divided by I. We take the momentum operator, apply it to a position ket. Again, it differentiates, only now it's the complex conjugate factor of I times h bar. And together, from these equations, we also find that the commutator of position operator and momentum operator is a multiple of the identity, namely I h bar times the identity. Now, here, if we were to exchange x by p and p by negative x, and what does this do to this commutator? Well, it would turn the commutator xp into the commutator of p and negative x, but that's the same as the commutator of x and p, because if I change the two operators in the commutator, I get a minus sign, so I change that, I get an extra minus sign, which removes the minus sign that I have introduced here. So if I have x and p, then I convert x into p and p into negative x. I get a new set of operators by this transformation, which are just as good as the original x and p. But that means that x and p are on equal footing. If I talk about position and momentum, and then by this transformation, position turns into momentum, momentum turns into position, which also means that what were position states before, if I do this transformation, they become momentum states. Which is to say that we also have momentum eigenstates, which, like the position eigenstates, will be normalized to the Dirac delta function. So we will have momentum eigenstates which are normalized in this sense with the Dirac delta function, and they will have a completeness relation, which is just completely analogous to the completeness relation that we had for the x states before, just like this is completely analogous to the brackets that we have for two x states, two position states. So what we can say about position bras, position kets, and the same must be true for momentum bras and for momentum kets, because the algebra of this position and momentum operators are such that we can convert one into the other without doing harm to the commutation relation. So the position and momentum have to be on analogous, on equal footing in this respect. Which brings us to the question how position kets and bras are related to the momentum kets and bras. Here we just know that if I take the ket bras from one set, integrate over them, I get the identity. I take the ket bras from the other set, integrate over them, I get the identity. But what is the more precise relation between the x kets and bras and the p kets and bras? And for that, we will consider what is called the xp transformation function. So let's call it the xp transformation function. It's the bracket of an X state with a P state. But before we go to this, we exploit this analogy a little bit further. Pay attention to this minus sign here and infer that there is a minus sign if we translate these relations. So if I have a momentum ket and apply position operator, then because of this minus sign that we have here, I will get I h bar d by dp, the momentum bra. And likewise, if I take the position operator and apply it to a momentum ket, I will get h bar divided by I d by dp, the momentum ket. Okay, so we'll have these relations. What happens when I take a position operator, apply it to a momentum bra, momentum ket? They supplement these relations about momentum operator applied to a position bra, position ket. And all we have made use of is this symmetry and the minus sign that appears here. So we are now going to make use of this by looking at this expression. So we want to know what is this. And for that, I will look at this expression in two different ways. Namely, one saying I have the position operator and I'm applying it to the position bra, so I get the number x, and then there is x and p. On the other hand, I take the position operator, apply it to the momentum ket, which is here, and so I get h bar divided by I d by dp of x and p. And so I now have a simple differential equation for the p dependence of this xp transformation function. And this differential equation, the derivative with respect to p is I divided by h bar x, tells me that, let me write this here, tells me that x e is equal to e to the I xp divided by h bar times a function that only depends on x, something that does not depend on p, because all the p dependence is here. So what is that function that only depends on x? Well, that will be the number that we have when p is equal to 0. Okay? So I differentiate with respect to p. That is the same as multiplying with I, dividing by h bar, and multiplying with x. That's what this exponential factor does. But then there is room for an overall factor that does not depend on p. Right. Now we repeat this game, only that this time I am looking at the momentum operator. And now the momentum operator applied to the position bra gives us h bar divided by I. But now I'm differentiating with respect to x. And as I apply the momentum operator to the momentum ket, I get the number p. So, again, it's a differential equation where it says you differentiate with respect to x, you get the function back, but multiplied by I and p and divided by h bar. That's, again, exactly what this exponential factor does. But now we have an extra factor that does not depend on x. So it is the value that we get for x equals 0 and arbitrary p. So the second differential equation is solved by this expression. Right, so what we find from these considerations is that the xp transformation function is this exponential factor multiplied by, well, either its value when p is 0 or its value when x is 0. Now look at this. This vector is a function of x and x only. This is a function of p only. So there's a function of x that has to be equal to a function of p, and that has to be true for all x's and all p, which simply says that these two functions have to be constants. So what we find is that the xp transformation function is equal to e to the I xp divided by h bar times a constant, and this constant is, if we look here, we can think of it as being the value for x equals 0 and p equals 0. Or one of them equal to 0, or the other one equal to 0, or both equal to 0. It's just a constant, okay? So now let's calculate this constant. All right, so we know that this xp transformation function is a constant times this exponential factor. And the constant, well, it's what you get if one of them is equal to 0, both of them are equal to 0. How do we find this constant? Well, we need to go back to the normalization. So let's, for example, look at the x prime bracket. And so with this completeness of the p states, we write this as an integral over p. Then we have the xp transformation function. We have the px prime transformation function, which of course is this kind of function, complex conjugate. So we have the constant from one of these factors, and then we have the complex conjugate of the constant, so we get the square, absolute square of the constant, and then we have the integral over p, and from this factor we have e to the I xp divided by h bar, and from this factor we have e to the negative I x prime p divided by h bar. And now I will make contact with something we had before by writing p as h bar k. And that gives us the following expression. So for the dp, we get a dk times h bar. So here is the constant squared. Then there is the h bar that I get from the dp. And then I have the integral over k. I will divide this by 2 pi and write a 2 pi factor here. And then we have e to the I k x minus x prime. The kx from here and the negative kx prime from there. Here is the delta of x minus x prime. Now the delta x minus x prime is the limit of any model of the delta function with epsilon to 0 through positive values. So what was that? Well, that was an integral of this kind, dk divided by 2 pi, a model defining function d, k epsilon, and then e to the I k x minus x prime, where at the end we have to take epsilon to 0 through positive values. All right, so compare this expression with this expression. And it basically tells us that 2 pi h bar times the constant squared has to be equal to the d k epsilon in the limit when the epsilon goes to 0 through positive values, but this is 1 as a property of the d. So what we conclude is that the square of the constant is 1 over 2 pi h bar, and it is therefore natural to write 1 over the square root of 2 pi h bar for this constant, because there is no benefit in being more complicated. I mean, writing I divided by square root 2 pi h bar or something else like this, or negative 1 divided by 2 pi h bar. Let's just write 1 over square root of 2 pi h bar, which is the usual convention that is always chosen for this factor. So now, having this transformation function at hand, we can see how, say, the position wave function is related to the momentum wave function. And for that, we just recall what is the position wave function. It is in the bracket of the position bra with the state ket. Now we want to relate this to the momentum wave function, then we have to use the completeness of the momentum states. And we do this in the obvious way. So there's the completeness of the momentum states, this relation here. There is the position bra, and there is the state ket. But now, here, we have the momentum wave function psi of p, and here we have the transformation function. So what we find is that psi of x is equal to the integral over p square root 2 pi h bar, which is this factor that we just found, e to the I xp divided by h bar psi p. And if we want to know the inverse of this statement, well, we start with psi of p, which is p, the bracket of the momentum bra and the state ket. Now we use the completeness of the position states. Which introduces the position wave function psi of x. And here we have the complex conjugate of this transformation function. So we find that the psi of p is related to the psi of x by integrating over x square root 2 pi h bar exponential minus I px divided by h bar, and then psi of x. So we have these two statements, one telling us what is the momentum wave function in terms of the position wave function, and one telling us what is the position wave function in terms of the momentum wave function. So the two wave functions are related to each other by Fourier transformation. So there's a Fourier transformation that turns psi of p into psi of x, and there's the inverse Fourier transformation that turns psi of x into psi of p. So as we can see, there is a lot of symmetry between position and momentum, and it goes back to the symmetry that we originally recognized in this commutator, where except for a minus sign we can interchange x and p, and this minus sign was important in recognizing a minus sign, a relative minus sign, as we translate from here to there. So as a reminder, we get h bar divided by I, the derivative with respect to x, when we apply the momentum operator to a position bra, and we get h bar divided by I, the derivative with respect to p, when we apply the position operator to a momentum ket. So it's this minus sign that we have here, which is responsible for sort of interchanging the roles played by bras and kets when we talk about position and momentum. And very important, the position and the momentum kets and bras are related to each other by this transformation function, which is a simple exponential phase factor. Okay, so for this motion for a particle along the x-axis, we have the wave function psi of x, we square it, multiply it by dx. That's the probability element for the vicinity of x, and we use it to find the probability, to calculate the probability of finding the particle in some range of x. And likewise, we have the momentum wave function psi of p, we square that, we multiply by dp. That's the probability element for the vicinity of p. So if we measure the momentum, we can calculate the probability of finding the momentum in some range by integrating over the corresponding p range. So for the example that we have studied before, where the psi of x, the position wave function, was the square root of positive parameter kappa e to the minus kappa absolute value x, and we had found, among other things, that the expectation value of x squared is 1 over kappa squared. Let's see what is the corresponding momentum wave function psi of p. So according to what we had established just a short while ago, we have the integral with the transformation function from an x state to a p state, which is e to the minus I px divided by h bar, and then there is this factor of square root 2 pi h bar, and here we have the wave function of x. So now for this particular example, there's the square root of kappa, the square root of 2 pi h bar, so that's an overall factor, and then we have the integral over x e to the minus I px divided by h bar, and e to the minus kappa absolute value of x. And this is an integral from minus infinity to infinity, which we break up into two pieces, namely integrating over the positive x values, in which case we have e to the minus kappa x and e to the minus I px divided by h bar. For the negative x values, that will give us a contribution where the sign of x is changed, px divided by h bar. So this is the term that comes from the positive x values, this is the term that comes from the negative x values, only that the integration variable is now positive throughout. So this is a simple integral. We get kappa divided by 2 pi h bar, and then the first integral gives us 1 over kappa plus ip divided by h bar. The second integral gives us the complex conjugate of that first one. So kappa divided by 2 pi h bar square root prefactor, and then combining this into just one term gives p squared divided by h bar squared plus kappa squared and 2 kappa in the numerator. So this is the psi of p that goes with this psi of x, and we can use it to calculate the expectation value of p and p squared. So without a calculation, we notice that the wave function is an even function in p. We square it is still an even function of p. So the expectation value of p will just be 0 for the same symmetry reasons that the expectation value of x was earlier found to be 0. And if we calculate the expectation value of p squared, and if we calculate the expectation value of p squared, we find that this is equal to h bar kappa squared, but I will not go through the calculation. I just leave this as an exercise. It's straightforward enough. Anyway, what I want to point out in this context is that the parameter kappa is such that the kappa is large, and then even for small x's, this exponential factor is very small. which means when kappa is large, the distribution in x is very narrow around x equals 0. And it's very tall there because the factor square root of kappa will also be very large. So if kappa is big, then the distribution in x will be very well localized around x equals 0. And there will not be a big contribution to the overall probability from large values of x. Correspondingly, the mean value of x squared will be small when the kappa is big. And conversely, when the kappa is small, then this distribution is very much spread out in x, and we will have a large value for x squared. However, it's the other way around for the momentum distribution. When the kappa is large, then we have large values of p prominent in the distribution, and we get a large value for the expectation value of p squared. When the kappa is small, the expectation value of p squared will be small. We notice here that the product of the expectation value of x and the expectation value of x squared and p squared, this product does not depend on kappa. It's equal to half of h bar squared. And that's a hint at a more general relation that we will consider next, and that will take us to the famous uncertainty relation that is associated with the names of Heisenberg and Kennard and others. In summary, we identified the momentum operator and recognized the profound symmetry between position and momentum that is visible, for example, in their commutator and in the position momentum transformation function. In the next lecture, we learn about the uncertainty relation for position and momentum.